now class, we're learning about derivatives of trig functions.
Yeah.
Derivatives of trigonometric functions. And we just did a little exploration to determine that. Here we have the cosine graph. For those of you in the viewing audience, we had y equals cosine x, and then we graphed the numerical derivative of cosine x, and we found that that looks like, okay, that, so here's cosine x, and here's negative sine of x, which seems to be the derivative of cosine x. So going back, what we say is that d dx, we already did this as a little exploration, of sine of x is equal to cosine x, and d dx of cosine x, even though it's not quite as intuitive, is negative sine of x. And then they have problems where they say find the derivative of this, find the derivative of that. So they might give you one where it says find the derivative d dx of x squared cosine x. So this is a case in which, what rule would I use? Product rule, okay? So the way we've been doing the product rule, it's the first left alone, right, times the derivative of the second. So it is the way I did it. Yes. So the first left alone, doesn't really matter which order you do the product rule in because it's addition anyway. But it's the first left alone times the derivative of the second, which is what? Negative sine of x times the derivative, or plus the derivative of the first, which is 2x times the second left alone. Okay? And then you can simplify that a little bit, and you get negative x squared, because you can pull that negative sign out front. Negative x squared sine x plus 2x cosine x would be the derivative of x squared cosine x. Okay? Can you just leave it like this? Like this? Yeah, you can leave it like that. That's good. That's good. What I did is I moved this in front because I don't like negatives as my leading coefficient. You could write this as 2x cosine x minus x squared sine x. It just looks a little nicer, right? Okay? All right. So let's do that. Is this easy so far?
Yeah.
Okay. Okay. Don't worry. It gets a little harder. I knew you were excited about that. Okay?
Yeah.
So the next thing they talk about is d dx. Find d dx of, now we have to apply the quotient rule of sine of x over 1 minus cosine, 1, sorry, no, it's not a 1, is it? 1 minus cosine of x. So in this case, this is a place where you have to use the quotient rule. So it's low d high minus high d low over the square of what's below. All right? So this is going to be equal to low d high. So here's low. D high, what's d high? Cosine x minus high d low. What's the derivative of that bottom? One what? No, 1, because what's the derivative of 1? 0. So it's negative, the derivative of cosine x, and the derivative of cosine x is negative sine x. So this just becomes what? Sine x over the square of what's below, which is 1 minus cosine x quantity squared. And then you could do some simplifying. All All right, and this one doesn't work out. I made this one up, so it doesn't come out as nice as the one that they got in the book. So you can do, oops, that's wrong, okay? Should be you distribute cosine x, this times this, minus cos squared x, minus sine squared x over 1 minus cos x squared. And then, since now you have to use some trigonometry. Remember trigonometry? Oh, trigonometry, sorry. Okay. Cosine. Okay. Minus, how could I rewrite sine squared of x? Do you remember? 1 minus cosine squared of x. Okay. Why would I want to do that? Because I think things are going to cancel out there and make it a little nicer. Okay. 1 minus cosine of x squared. And so now I have a minus cosine squared of x and a minus minus cosine squared of x. What happens? This thing would go away with this because it's a minus, so it makes a plus. So on the top, I have cosine of x minus 1 over 1 minus cosine of x squared. And I guess you could simplify that more by multiplying, distributing, and multiplying through by -1, but I'm not going to. That's good enough. Okay? Okay? We're good?
So it would be okay if we just left it like that?
Yeah, if you just left it like that. Like what they might do in the book, what they might do is they might say this is equal to negative cosine of x minus cosine of x minus 1 over negative 1 minus cosine of x times 1 minus cosine of x, because that's what cosine, and all I did is I multiplied the top and bottom by -1. What that lets me do, that lets me change this into 1 minus cosine of x. See? Because negative times that, and then what would happen is you can cancel out this with one of these, and what you have is 1 over negative, because I distributed that, negative 1 minus cosine x, which is the same as 1 over cosine x minus 1. There might be an easier way to go about it than that, but that's the best way. That's the best answer. But if you gave me this answer, I guess I'd be happy with it. Okay? Do you understand the little tricks I did there? That was kind of tricky algebra. So you get something to flip, you have to multiply the top and bottom by this. Okay?
Well, we don't have to do that.
No. Do you have to know? Maybe. Not on my test, but maybe an AP test or something. So then they have this thing about simple harmonic motion, and what you saw last year. Simple harmonic motion. And girls in the back. Shush. So, and they have this problem, a weight hanging from a spring, hanging from a spring, and this is with no friction, I guess, and it just goes on forever and ever. From a spring is stretched, and I know we all did this in pre-calc last year, 5 units past its rest position. So, and it's modeled by the equation S of t is equal to 5 cosine t. So this is the position function. Position. So, and if you remember, you kind of have this little spring kind of going down like here, and then there's, let's keep going, and there's a weight down here, and here's like the equilibrium position over here, okay, and here's here is find the velocity and acceleration, and so it's pulled down, so this would be 5 units, and so it's pulled down this way, and then it's going to go up. So if I were to plug in, like for instance, I don't know, 2, I'd get out where that thing is at that point. Where this is actually, this would be negative and this would be positive, right? Okay. As far as distance from the equilibrium position. Okay, position from equilibrium. Okay, and equilibrium. And they'll say find velocity, and acceleration functions. Could you do that? What's the velocity equation? S prime of t, right, is going to be equal to the velocity, which is negative 5 sine of t. Do you guys understand that? Yeah? Maybe? Because the derivative of cosine is negative sine times 5 gives you negative sine of t. What's the acceleration equation?
Why do you still have the t?
What?
Why do you still have the t? Because it's times, so you still have
Yeah, because it's not product rule anymore. I mean, it's not power rule anymore. So derivative of cosine x is just sine x, right? Or negative sine of x, right? So the derivative of cosine t is negative sine of t. There's still a variable there, all right? And so the 5 comes and stays in front because it's just a constant. So s double prime of t is equal to the acceleration. So you have to take the derivative of the velocity. What's that? Negative 5 times cosine t. And if I wanted to, I could find s triple prime of t, which they say is called the, anyone know Mr. Lowe told you this? This is called the jerk. Okay? Jerk. That's equal to the derivative of this, which is back to 5 sine of t. And what they talk about with jerk is like how fast the acceleration is changing, right? And they said, what's the derivative of our acceleration here? If you drop a ball from a height, what's acceleration due to gravity? 9.8 meters per second, or 32 feet per second. What's the derivative of that number? What's the derivative of 32 feet per second?
60.
What's the derivative of a constant? 0. Okay? So this thing called jerk, okay, if you take the derivative of acceleration, is 0, right? And so that's why if you're in free fall, you're just kind of hanging out, you're kind of playing, right? You're not really feeling anything moving around, right? If you're in outer space, because the acceleration isn't really changing, even though you're moving really fast, okay? But you might still be accelerating, but you're just accelerating at a constant rate, something like that. But like when do you feel like that? When do you feel like you're jumping around? When you're jerking? On a what? On a trampoline, like in rides and amusement parks and stuff, because you're not only is the velocity changing really quickly, but your acceleration, right? You're going from a I don't know, really steep thing to really, you're jerking around or on a bus, it's like, it's not constant acceleration, you're going, like that, and that's called jerk, and that's why it's called jerk, because your acceleration is changing really rapidly, okay? Jerk is sudden change in acceleration, third derivative of position. Okay, so they talk about gravity and stuff like that. So, so for instance, with this function, if I were to graph, the original equation over here, which is 5 cosine t, which looks something like this, right? 5 cosine, so this is 5, and this is negative 5. And velocity, I did that right? Sine, cosine, 5 sine of t. And I were to graph 5 sine of t, which looks like this, right? And like this, and like this. Where is, if this is the jerk, okay? What a jerk, okay? If this is the jerk equation, where's my jerk at a maximum? My jerk is at maximum when this thing is what? 0. What's my spring doing at this point? It's going through the equilibrium, which kind of makes sense because it's going like from going as fast, it's going from really fast to slowing down, right? So it's kind of like you're in an elevator, you know elevators, right? And you know how at the beginning of the elevator, it's kind of like, you know, you go like that, there your acceleration is changing pretty rapidly, right? Or when you stop. And I thought about that, I would think maybe the jerk would be greatest right there. But the jerk there looks like 0 because, right, when I get to here, what's happening to the velocity of my spring? It's, what is it at the very top?
0.
Right, when I go all the way up, it's kind of slowing down, right, because it starts at 0, right? It starts with a 0 velocity, and then the velocity gets faster, faster, faster. This isn't a graph of velocity, this is a graph of the distance from the equilibrium position. Anyway, so up here the jerk would be 0 because you're kind of like slow down really gradually and then you go back down, right? You know what I mean? Kind of here at the top of the Ferris wheel. Very good. So you're going around and then it's something like that. Okay, so that's jerk. So it's graded. Okay. So let's find some other derivatives of trig functions. What's d dx of tan of x? Anyone know that already? Do you think it's cotangent of x? It's not. I have no idea. Okay. How about if I derive it for you? And then I'll just give you the rest of the ones that some of your homework says derive the derivative of cotangent of x or secant of x or something like that. What is it? It is secant squared of x. But this is going to be, let me just derive it for you to show you where it comes from. Tan, remember, it can be written as sine of x over cosine of x. Remember that? From last year?
Yeah.
Yes, good. Okay, so I'm going to take the derivative of that using the quotient rule. So it's low d high, which is cosine x, right? Low d high minus high d low. What's d low? Negative sine of x, right? Over the square of what's below. Cosine x squared. And this can be written as cosine squared x plus sine squared x. Oh, look at this. Whoops, not sine x squared, sine squared x over cos squared x. Does anyone remember what cosine squared x plus sine squared x equals? 1 over cosine squared x. That's why you did all that identity stuff last year. What's 1 over cosine squared x equal to? Secant squared x. This is trig stuff, okay? So the derivative of tan of x is equal to secant squared of x. Okay? deriving the other ones is an exercise left to the student. Okay? So the derivative of cotangent of x is cotangent of x is not actually cosecant, it's negative cosecant squared of x. And you could figure that out in a homework problem. Okay? The derivative of secant of x, derivative of secant of x is equal to, I'm going to remember this, secant x tangent x. And that can be derived pretty easily too. Okay? And the derivative of cosecant x, I'm going to double check me to make sure I got all this, is negative cosecant, 90% sure, 99% sure. I remembered these from teaching this. Negative cosecant x cotangent. You need to know those, okay? So you need to know the derivative of all these 6 trig functions. And whether you know sine of x and cosine x, if you know sine of x and cosine x, you can always derive the other 4, okay? Or you can just memorize it, all right? I can show you, if I have time, the derivation of these ones. Pretty straight. You just change this into, what's secant equal to? 1 over cosine, and then you could use the quotient rule to try to figure out the way that works. Okay? So, what else? So let's do a problem. Find the equation. Hey, and then I'll be done already? Oh no, will I be done? That's not enough. Wait, did I lose my 3rd page of notes? Oh, right now. Okay, so which one? Find the equation of the tangent line to y equals tan of x over x at x equals 2. So this is kind of calculator-ish, all right? And so I would like to do this derivative for you, but then we could just plug in your calculator and show you how that would work too, okay? So y prime is going to be equal to ODI x times secant squared x minus high d low tan of x over times the derivative of times
Just over.
because the derivative of x secant squared of x tan of x times the derivative of what's below, which is 1 over x squared, right? And then, so what you have to do is plug 2 in there, and you get out. Yeah, because this is times 1, right? Because the derivative of x is 1, right? So when I plug 2 in there, I get out about something, okay? And so you could do that with your calculator. You can go second, clear. What I'm going to do, I'm just going to plug in tan of x over x into my function. Okay? Tan of x, tan of x divided by x. And, whoops, I didn't put that into y equals, did I? Y equals, sorry, tan of x close divided by x. Now, rather than plug in that horrible derivative that I just found, I wanted to show you that derivative. But all I'm going to do is now I'm going to go second quit, and I'm just going to plug in clear. I'm going to plug in, take the numerical derivative of tan of x over x at 2. So I'm going to go to math. I'm going to go to 8. I'm going to go 2 bars. I'm going to go to y bars. I'm going to go to function. I'm going to go to y1. And I'm going to go comma x. And in this case, you're going to plug in comma 2. Comma 2. Got it? And I'm going to hit enter. And I got to make, and that's the answer you're going to get. So that is the slope of the tangent line to this curve at 2. Okay, slope of the tangent line, not the tangent line itself, but the slope of the tangent line. And then what I'm going to do with that number, I'm going to bring it to the step. The store. I'm going to store it as alpha A, because you don't want to round those things off too much until the very end. Okay, so I'm going to store it as alpha A, and then I'm going to hit enter. Okay? And then what else I need? I know I need a point. I have the slope. I need the point, and I know that the x-coordinate of the point is 2. So I'm just going to plug in 2. I'm going to go, I want to find the value, right? So I'm going to go bars, how do you do that again? Bars, y bars, function, y1, and you want y1 to just do like this, 2.
Mr. Leader, can you just trace it from the graph?
Yeah, but you want to put it into storage. So you want to store it, and tracing isn't very accurate.
Well, can't you go like
Second cal. Yeah, I guess you could do that too. But you also want to store it. Okay? And if you hit enter, that's what you get. So that's y of 2. And then I don't need to store that right now. So now, if I'm going to write, if you want to unstore, the reason they have you store it, at least in the book, is because in this dumb book, I have to change this view, always, view options, always in front, okay? Now I can write on it. Oh, good. So now your tangent line is just going to look like y minus negative 1.092, take it to 3 decimal places. So that'd be 93, right? 93 equals m, which is 3.433x minus 2. So that'd be the equation of tangent line, which is y plus that, right? 1.093 equals 3.433 times x minus 2. Now in the book, they tell you to leave these in the storage until the very end, because what they want you to do is multiply this non-rounded off number times this and add it or subtract this rounded off number so you get the equation in slope intercept form. Okay? That's why we use the storage key to store those big, long, significant digits, because you don't want to round off until the very end. You know, because if you round off now and then you add, you multiply this through, and then you subtract this, you're going to get a more rounded off answer. So you want to wait till the very end to round things off. So I could do that. I could go y minus, I would store that as b. So y minus b equals a times x minus 2. And then if I want to get it into slope intercept form, y equals ax minus 2a plus b. Do you guys see where that came from? Okay. I just distributed this times this times this gives you 2a, and then I add the b. And then you could go into your calculator and figure out what minus 2a plus b is, and you'll get an unrounded, you get a nice, neat answer, and then you round off at the very end. You see? Okay?
Like how far should we have that?
What?
Like how many decimals?
3 decimal places. 3 decimal places. Okay?
So do we have to start going through the point or something? That's like you said.
I will make you on a test, but in the book, and on the AP test, they won't make you. Okay? But in the books, they do. Okay? So a lot of times, so you'll be looking for the answers, you know, and you won't find them. It won't look like that. Okay. And then last thing, and then I'm done. Oh, thank goodness. All right. So, so the last thing, if f find f double prime of x. Oh no. If f of x equals secant x. F of x equals secant of x. Okay? So the first thing you have to do is find f prime of x. What's f prime of x? Secant x tangent of x, and then you have to find f double prime of x. So now you have to use which rule? Product rule. So you take the derivative first, which is, so this is like, here's the first function, so it's kind of like this, right? This times this. So you have to take the derivative first, which by itself is secant x tangent x, times the second, which is tangent of x, plus the first left alone, which is secant x, times the derivative of the second, which is what? Secant squared x. Okay? And then you simplify. Secant x times tangent x makes secant x tan squared x. Right? And secant x times secant x times secant x makes secant cubed x plus secant cubed x. And then I guess you could just leave it like that. They might ask you to factor out, oh, could we do this? Let's just leave it. I guess you could factor out a secant x times tangent squared x plus secant squared x. I think that's equal to something, isn't it? What's tangent squared x plus secant squared x? Is that's not 1. No, it's not. I think tangent squared x minus secant squared of x is but not. So I think you just have to kind of leave it like that. Okay? But they'll use, I think it's minus, if I remember. Okay? Okay, so that's the end. And your homework is page 146, 1 through 23 odd. And I'm just kind of hand-picking these problems rather than looking at what they suggest. 26A. I don't know why it just chose 26A. I'm sure there's a reason for it. 28, 31, 33, 37, 39, and 46, 48, and 49. And 49. And that's it. And that took 34 rolling minutes. And remember, you heard it here on Mr. Leader's Leading Edge YouTube channel.
Yeah.